We ended part 1 with a simple question. If the Boots void shouldn't exist this cleanly, then what could explain it? Now this is where most stories get lazy. They pick one explanation, treat it like a verdict, and move on. We're not doing that, because when scientists looked at this hole, they didn't find one neat answer waiting at the bottom. They found a list of possibilities, some boring, some plausible, and some that feel unsettling for a completely different reason. And here's the important part. Even the boring explanations don't fully remove the discomfort. They just change where the discomfort lives. So in part 2, we're going to test the explanations the same way a good investigator would, one by one, in the order your brain naturally reaches for them. We'll start with the safest idea. Maybe this is just rare luck. Then we'll move to the skeptical idea. Maybe we're being fooled by the data. Then we'll go deeper, back toward the early universe, where the explanations start implying something bigger about how structure forms at all. And finally, we'll confront the most unsettling truth of this story. No matter which explanation you prefer, the void still survives. Because the Boots void isn't just an empty region, it's a stress test. A blank patch on the map that forces you to ask whether the universe is more capable of extremes than we're comfortable admitting. All right, let's open the first door. So what could cause a hole this big? This is where people usually split into two groups. One group wants the dramatic answer, something exotic, something broken in physics, something that shouldn't be there. The other group wants the safe answer, a rare but normal outcome of a universe that's simply too large for human intuition. The truth is, scientists explored both paths, and to understand why the Bootes void still has power as a mystery, you have to walk through the explanations in the order they were tested, because each one sounds convincing until you meet the problem hiding inside it. Let's start with the boring door. Explanation number 1. It's just cosmic variance. In plain language, the universe is messy. If you zoom out, it averages out, but locally, it can still do weird things. A giant void might simply be the result of chance, an unlucky region where the early universe started with less matter than usual, and gravity never had enough seed material to build many galaxies. This explanation is attractive because it doesn't require new physics. It says, this void is rare, but the universe is enormous, so rare still happens somewhere. The problem is the word somewhere, because the Bootes void isn't just a little weird, it's weird in a very specific way. The combination of its size and emptiness feels extreme. Cosmic variance can produce odd patches, but the bigger the patch, the harder it becomes to stay odd. That's the averaging out intuition again. So yes, cosmic variance could be the answer, but it's the kind of answer that leaves you unsatisfied, because it doesn't explain why this one looks so clean and so huge. It explains it the way a shrug explains a mystery. Now we go to the next door, the one that every skeptic pushes first. Explanation number 2. We're being fooled by the data. This is the responsible question. What if the void isn't real? Maybe galaxies are there, but we can't see them properly. Maybe our surveys missed faint galaxies. Maybe dust or foreground interference is blocking our view. Maybe we're making a map from incomplete information, and that incompleteness happens to land in the same region. This is where people expect a dramatic aha, because it's comforting. It means reality stays normal and the mystery dies. But here's why this explanation doesn't erase the void. Astronomers didn't just look once and call it a day. They compared different surveys. They looked deeper. They checked whether faint galaxies were being undercounted. And while details can change depending on the data and methods, the core oddity persists. That region is still underpopulated compared to what you'd expect if the universe were behaving normally there. In other words, the void may not be perfectly clean at the edges, and the exact boundaries can be debated, but the emptiness doesn't vanish. So, bad data might soften the void. It doesn't delete it. And that pushes us into the more interesting explanations, ones that start at the beginning. Explanation number 3. The early universe started with an unusually deep underdensity. This is the explanation that sounds simple but carries the most weight. If you want to build a cosmic whole, you don't start late, you start early. Remember the cosmic web idea? Tiny differences in density after the Big Bang grow over billions of years. So what if the patch that became the Boötes void didn't start slightly underdense? What if it started very underdense, not empty, just missing the initial material that most regions had? Over time, gravity would have less to work with. Fewer galaxies would form. Matter would drain away toward denser regions. The patch would expand into a void. That mechanism is real. It's not fantasy. The unsettling part is what it implies, because it suggests the early universe might have had rarer, stronger fluctuations than we like to assume. And if those fluctuations can be that strong, then extreme structures might not be accidents at all. They might be baked into the universe's starting conditions. But here's the catch. If you push this explanation too far, you bump into other observations. If one region is drastically underdense, that kind of imbalance can leave traces in other cosmic signals, especially in the oldest light we can observe, the cosmic microwave background. Now, I'm going to say this carefully because this is where people exaggerate. There have been discussions in cosmology about whether very large voids could be connected to large-scale temperature anomalies in the cosmic microwave background. Because light traveling through an underdense region can gain or lose a tiny amount of energy as the universe evolves. It's one of those effects that's real in principle, but hard to measure cleanly in practice. So you'll sometimes see the Boötes void mentioned in the same universe of ideas as cold spots and other large-scale anomalies. The responsible way to say it is, it's been considered as a possible piece of a bigger puzzle, not proof of anything by itself, not an alien fingerprint, but a reminder that voids aren't just empty space. Voids can affect what we observe. Still, even if you accept deep, early underdensity, there's a problem. It explains why the region is emptier, but it doesn't fully explain why it's this large and still looks so extreme compared to surrounding structure. So we move to the fourth door, which is weirdly satisfying because it reframes the whole question. Explanation number 4. The void is shaped by what surrounds it. Walls make it look even emptier. Think of a bubble in foam. The bubble isn't just an empty region. It's defined by the foam walls around it. In cosmic terms, voids don't sit alone. They're carved out as matter collects into filaments and walls. So one possibility is that the Boötes void is not just one emptiness. It's emptiness exaggerated by architecture. Maybe the region is surrounded by unusually strong structures, walls and filaments, so that matter was funneled out more efficiently. Maybe the void is made of smaller voids that overlap, creating one giant, underdense region that looks cleaner than it really is. Maybe our human habit of drawing boundaries turns a complex, underdense area into a single, bold whole. This explanation is powerful because it turns the void from a glitch into a consequence. Not, why did nothing form here? But, why did everything around it become so structured that this region became the leftover? The problem is, even this explanation doesn't completely calm the nerves. Because if the surrounding structures are strong enough to create a void that extreme, then the universe still did something extreme. You've just shifted the extremeness from the whole to the walls. And that brings us to the uncomfortable conclusion. Each explanation can soften the mystery. None of them erase it. Cosmic variance says, rare happens. Data bias says, maybe it's not as clean as it looks. Early underdensity says, it started emptier than normal. Surrounding walls say, structure carved it out. But the Boötes void still sits there, like a blank space on the map that refuses to stop being blank. Which is why, after all the surveys and all the models, this is still a story worth telling. Because the deeper question isn't, is the void real? The deeper question is, what does it teach us about how the universe builds structure? And that's where the Boötes void becomes more than a curiosity. It becomes a warning. None of these explanations feel complete. Here's the twist that changes how you see the Boötes void. The Boötes void is not interesting because it's empty. It's interesting because emptiness is information. In a universe where gravity is doing the construction, the places where galaxies didn't form can tell you just as much as the places where they did. Most people think cosmology is about hunting for objects, black holes, galaxies, clusters. But the modern universe is a pattern problem, a structure problem, and voids are the negative space that proves the structure is real. Think about a fingerprint. The ridges matter, but the empty gaps between ridges matter too. Without the gaps, the print has no shape. Voids are the gaps in the universe's fingerprint. So when a void looks too large, too underpopulated, too clean, it doesn't just challenge one area of sky. It challenges the rules we use to interpret the entire map. Because every cosmological model you've ever heard of, everything from dark matter scaffolding to the way galaxies cluster, depends on the statistics of structure. How lumpy is the universe? How smooth is it on large scales? How often do extremes appear? Those aren't abstract questions. They're the foundation for how we estimate the mass of the universe, the behavior of gravity, and the way matter moved from the Big Bang to now. And this is where the Boötes void becomes dangerous, in a scientific sense. Because when you see a void this extreme, one of two things must be true. Either the universe is more capable of producing extremes than our intuition expects, or our measurements and assumptions about large-scale structure are missing something. Now let's be clear, that doesn't mean physics is broken. It means the universe might be better at surprising us than we want it to be. Here's one unsettling way to think about it. When cosmologists run simulations of the universe, they don't simulate every star. They simulate matter as a kind of fluid, dark matter and normal matter evolving under gravity. Then they see what structures form. The cosmic web emerges naturally. Voids emerge naturally, and those simulations are one of the reasons we're confident we understand large-scale structure. So when you find a void that feels too extreme, you're not just questioning a dot on a chart. You're questioning how closely the universe matches the simulations we trust. Because if the simulations underpredict how extreme voids can be, then they might also underpredict other extremes. And that's where the Boötes void becomes a gateway. A gateway to questions like, how much of the universe's structure is determined by early conditions we can't fully measure? Are there rare fluctuations in the early universe that are more important than we think? How does dark matter behave in the emptiest regions? And, this is a quiet but important one, how do we know our average universe assumptions hold when the universe is vast enough to hide surprises? In other words, the Boötes void is a reminder that the universe is not obligated to be intuitive. Now, here's the part most people miss. Voids aren't just passive emptiness. They evolve. As the universe expands, underdense regions can expand faster than overdense regions. Matter drains out toward the surrounding filaments and walls. So over billions of years, a void can grow. Not because something is eating galaxies, but because gravity is collecting matter elsewhere. That means voids are not just the absence of galaxies. They're the aftermath of a long gravitational story. A story where matter got pulled away. And that gives the Boötes void its final sting. Because if this region truly is as underpopulated as it appears, it means that on cosmic timescales, gravity successfully evacuated a vast volume of space. Not perfectly, but dramatically. Like the universe decided to move its matter out and build walls around the edge. And when you picture it that way, the void stops feeling like a hole in space and starts feeling like a hole in the distribution of matter itself. Like a missing piece of the universe's scaffolding, which leads to the real twist. The Boötes void doesn't just make you ask, why is this empty? It makes you ask, how many other impossible structures exist that we haven't mapped yet? Because the cosmic web is not fully charted. We're improving our maps, but our picture of the universe is still incomplete. We are still assembling the puzzle. And the Boötes void is one of those pieces that doesn't quite fit the box art. It's not proof of aliens. It's not proof of a broken universe. But it is proof that the universe can produce patterns that feel like glitches in reality. And if a glitch can exist on that scale, the most honest response isn't fear. It's humility. Because it means the map isn't finished. So what is the Boötes void really? It's a region of space that's not supposed to feel this empty. Not because emptiness is forbidden, but because the universe on scales this large is supposed to average out. It's supposed to be statistically calm, and this isn't. It sits there like a blank patch on a cosmic map, refusing to behave like a normal bubble in the foam. Now, if you're hoping for a clean answer, something you can file away and forget, this is where the universe gets annoying. Because the most honest answer is this. The Boötes void probably isn't one thing. It's not a monster. It's not a single object. It's not a cosmic accident with a dramatic cause. It's a consequence of how the universe builds its structure, pushed to an extreme. A region that started underdense, then got emptier as gravity did what gravity always does. It moved matter toward where matter already was. It drained a vast space and built walls around the edges. And if that's true, then this void is not just an emptiness. It's a fossil of the early universe. A leftover imprint of whatever the universe was doing in its first moments. An imprint that survived billions of years of expansion and evolution. That's what makes it unsettling. Because a fossil like that doesn't just tell you about one region, it tells you about the rules of the entire game. It tells you that the universe is capable of producing extremes that feel wrong to human intuition. And once you accept that, you start looking at the sky differently. You stop seeing space as a calm background. You start seeing it as a structure in motion. Threads, walls, knots, and gaps that might be just as meaningful as the galaxies. A cosmic architecture where emptiness is not nothing. It's a clue. And maybe that's the real reason the Boötes void sticks in the mind. Because it doesn't feel like just empty space. It feels like a missing piece. A place where the universe should have written something and didn't. And if a hole this large can exist, then the next question is obvious. What else is hiding in the negative space? What other patterns are sitting in the sky right now, real, measurable, enormous, waiting for us to notice them. Because there's another anomaly in the universe that feels like the same kind of warning, except it's not a hole in galaxy maps. It's a scar in the oldest light we can see. A cold patch in the cosmic microwave background, the afterglow of the Big Bang that looks too large to ignore. Some people think it might connect to structures like voids. Some think it's something else entirely. Either way, it's the kind of mystery you don't forget once you've seen it. So if you want the next chapter, the next unsettling map glitch, in the next video, we're going to talk about the cold spot, a bruise on the sky, a region of ancient light that looks wrong. And we're going to ask the same question we asked tonight. Is it a coincidence? Or is it evidence that the universe is stranger than our models allow?